It's not the same. Plus, our book has, the review book has like the.
All right, guys,
31, but sorry.
look at some more accounting principles.
Circular.
Everybody's favorite. Okay. So. All right. So right here, I want to ask you a question. If I had 3 items that were different and I lined them up in a row, how many different ways could I arrange them?
Or
3. There's 6, right? I could have, if it was called A, B, C, for instance, I could have A with B and C or B, right? I could have B and then A or C or A, or I could have C with A or B or A. And that's 6 different ways. You don't even have to think that way. You could just say there's 3 ways I could put it in the first spot. Once that thing's in there, there's 2 remaining ones, right? And then once that one's there, there's only 1 remaining for the last spot, 3 times 2 times 1, using that fundamental counting principle. Now, things change when I arrange them on a circular situation. I want you to hear this. If you don't hear it, I will show no mercy on you on your test. Now, when you arrange things in a circular way, and I want to preface circular, doesn't really have to be circular. I could have 10 people around a circular table. I could have 8 people on an octagonal table. I could have 4 people on a square table. The idea is this. When they're surrounded in some kind of a ring, which I'm just calling circular, the way you count changes. And I'm going to demonstrate that. I have a table here with 3 people, person A, B, and C, sitting at different spots. And I want to show you that these are all kind of different, right? From the standpoint of if I have A here, right here where I'm pointing, I have C to the left, B to the right. Here I have A in the same spot, but B to the left, C to the right. Here I replaced person A with B. Now I have A to the left, C to the right. Kept B where they is, C to the left, A to the right. Then I replaced B with C, A to the left, B to the right, B to the left, A to the right. So it appears that there are 6 unique situations, right? There's really only 2. Now let me talk about this for a second. In a circular situation, what we're saying is, in the absence of the surroundings having an impact. Now, surroundings do often have an impact. Like if I go to eat with my wife and we have a table for 2, how many ways are there to sit down? To me, 1. We sit down and we order, right? But for her, it's like, I'm not sitting in that chair because that faces the wall. I'm sitting in the chair that faces beauty because she's an artist and she sees that stuff. To me, I see it, but I don't appreciate it like her, so I'm like, just sit with this. Okay? But my point is, if you consider surroundings, there's a definite difference. It's like right here in this room. If you sit near the back corner right here, closest to the door, you're probably going to get asked by me to shut the door. Okay? If you sit here, right here in the front, you're probably going to have to move your feet in. Okay? Certain situations on the perimeter often affect that. But if I have a situation that is not affected by that, okay, and it's circular and there's no talk about, oh yeah, well, this person has to go to the bathroom really bad and there's the back entrance right there, they can sneak out to the bathroom. So yeah, being closer to the back. Or how many people show up to something and they're a little bit late and they sneak in and they sneak in the back? It's a little bit easier. Right? The order in which that happens could be impacted by external situations. But if it's not, and it's circular, these 6 ways really shrink down to 2. So let me show you. For instance, person A has C on the left and B on the right, correct? What's going on right here with this person A? C on the left, B on the right. So that number 3 is the same as that number 1 when you consider the order. If you think about it, if you think about person C and the conversation they're having, it feels the same, right? C on the left, B on the right. So I don't need to count that. And then if you look at this A right here, C on the left, B on the right. In the absence, I can take that just by turning it and make it match all 3 of these. So those two, why overcount them when they appear to be the same as this? And then if you look at this one, if you look at person A, B on the left, C on the right. Well, look at this A, B on the left, C on the right, B on the left, C on the right. Those two, just by turning this and turning it again, have the same perspective at that table. So these 6 options, these 3 factorial options, just got reduced down to 2 factorial options. So whenever you have a circular situation, now there are things that appear circular that lose their circular nature. We'll talk about that in a couple seconds. But if you have a circular situation and there's nothing that impedes your ability to turn it to create something that looks different, then I don't say 3 factorial when I count like I would if it was linear. I would say 3 minus 1, then factorial, or n minus 1 factorial. Are you with me so far? Now, what if I said, hey, on this particular situation, there was a giant column right here going straight up. I guess columns are on the ground. There's this giant column right here at the top of the table, okay? So every one of these, there's a giant column right there at the top of the table going from the ground up to the ceiling, right? It's kind of an annoying column, but maybe the table is pushed right up against it. Now think about the perspective of this room. Does person A have C to the left, B to the right still? Yeah, but they got the column to the left. You look at this right here, person A has C to the left, B to the right, but now the column's to the right. Person over here has C to the left, B to the right, but now the column's opposite. The perspective was changed by that. Are you seeing that? Okay, so right here, if there's anything that is impeding the ability for me to rotate this and it look exactly the same, with the exception of the impeded part can't rotate. If it's stuck there, then I lose the circular nature of it, and this circular thing that was now becomes, I know that's a horseshoe, but that becomes linear again. Because now ABC, ACB, BCA, BAC, CBA, and CAB all are different in relationship to that fixture. Are y'all seeing this? So oftentimes you'll have a situation where a problem will say, and I would have loved to do this with 4, but 4 requires 4 factorial demonstrations, which is a huge page of diagrams, and I was like, I got started getting tired when I did this. So anyway, I do want to show you what would happen in a slightly different situation than that. Like, what if I said, all right, guys, there are 8 chairs surrounding a table, okay? 1, 2, 3. That's 8. Come on. Oh, man. Okay. So there's 8 chairs around a table, right? 7 people need to be arranged, but we have to keep that one open in case Fred comes in later, whatever. Okay, that one has to be kept open, that specific chair. Okay, so if I said that, and I said, all right, how many ways can I arrange these 7 people? Well, those 7 people are not getting arranged technically on a circular situation anymore, because this impeded that nature. It has to be left open right there. So really, I'm coming in here and I'm arranging people on these 7 chairs, right? And again, those 7 becomes linear. I would say 7 factorial. You track with me? And it gets really odd in some cases. What if I did this? Like, what if I said, all right, I've got 8 people that I want to arrange. This is really bothersome to a lot of people's brains, but I'm just trusting the probability. If there's 8 people I'm going to arrange, and one of them's name is John, this kind of gets into conditional counting or probability, although it's not a probability problem. And one of those people is John, and I'm sticking John right here. he has to be fixed, right? So how many people am I arranging? 7. So John has to go there, but the 7 people I arrange, if John has to get in that seat, still end up being where? Linear, because they're being arranged in those. So it still becomes a 7 factorial situation, even though I started with 8 people. So at the end of the day, you're like, wait, if I had 8 people, but one of them, John, has to go in there, you're thinking, because it's circular, 8 minus 1 factorial, which is 7 factorial. But I put John there and the rest is linear, so it still ends up being 7 factorial. And that bothers people, and they're like, wait a minute. So it's the same factorial whether I put John there or whether I just arrange 8 people circularly. Yes. And that might bother you a little bit, but if 8 people, if one of them goes there and there's 7 left over, those 7 left are being arranged in those, that is impeding the circular nature of this 7 factorial. Okay? Now, this kind of situation shows up in a lot of situations, like around the table. But sometimes it shows up in a circular way. It's also flippable. Like, for instance, if I was wearing it, and I realize this is not true for every necklace or every bracelet or charm bracelet or whatever, but or key ring. Let's just say I had a ring of keys, okay? And I had key A on there. I had key, whatever, B on there. Let's just say they were double-sided keys here. And then I had key, nowadays you have push buttons. People won't even pull the keys out half the time, but on my old car, I still have a key. So right here, if I had a key ring with key A, key B, key C on it, and right here, I would not say, if somebody asked me, how many different ways could you arrange that? Because this is a lot like the table, isn't it? And the table would suggest, if it's circular, like if I wanted to get, for instance, if I wanted to have BCA instead of ABC, I could just take A and swing it over there and I'd have BCA, wouldn't I? I don't count that as a different arrangement. I put the keys on the same way. I still ended up with BCA. I could also end up with CAB that way. Taking C, swinging it over here. There's CAB because it's circular in nature. So how many unique ways are there? Not 3 factorial, but what? 2 factorial. But here's the thing. Because it's a key ring, I can also flip it, right? I mean, you ever pick up your keys and go, oh, pick them up backwards. I mean, if it's a set of keys, it's a flippable situation. Like there's the anticlimactic. Hello? She is? No, I'm just kidding. I said. All right, so I'm going to bring us back to that table situation. Right here, check it out. Okay, so back to the table situation. Initially, I had said that this one was like 2 of the others, and this one was like 2 of the others, right? So really, we were saying the only 2 ways you could really arrange people around the table and have a different perspective, if the exterior stuff didn't matter, were these 2 ways, right? Now, pretend these are keys. It looks different right here. C on the left, B on the right. Here's A, B on the left, C on the right. But what if I pick this up and flip it over? What do I have? That, right? Like if I'm holding key A and I just spin this around, now C is over here and B is over there. So if it's flippable, that takes half of your results and throws them away. If it's circular, it reduces by 1 before you factorial. If it's flippable, it divides by 2. So if these are 3 keys on a key ring, I certainly don't have 3 factorial ways to do it. I have 3 minus 1, but because it's flippable, I go down to 2 factorial divided by 2, and now technically there's 1 way to put 3 keys on a key ring. Now there are other facts, which means if I gave you key A, B, and C, and I gave you a key A, B, and C, and you a key A, B, and C, I gave everybody in the room a key A, B, and C, and I said, put them on any way you want. And you put them on there, and you're like, all right, this is so different than everybody else. All right? I could take every one of those just by rotating them around or flipping them and make them all look identical. Now, I can't do that with 4 keys, because 4 keys on a key ring would not be 4 factorial, it would be what? 3 factorial divided by 2. And that 3 factorial divided by 2 would be 6 divided by 2, which would be 3. But if I gave it to everybody in the class, I could make everybody's keys look like one of 3 options just by either flipping the key ring over or moving stuff around. Now, I realize that people might say, yeah, but if you flip the key ring over, then maybe the key doesn't work in the car the same way, or whatever. Yes, but those are things that were not included in my problem. Okay? So these are very generic situations that you will see about flipping and circular. But just remember, the circular nature means nothing can impede it. So people that wear a necklace, which maybe some dudes, maybe some girls, I don't know what you have on that necklace, but let me ask you a question. Can I go back to the key thing? Like, say these were 3 charms on a necklace. If I take B or C and I swing it around to the other side, but there's a clasp right there, what happens? It either doesn't go because it hits the clasp, or it carries the clasp around to the front looking stupid, right? Unless you want the clasp to be in the front. But my point is, if the clasp stays in the back, what is that doing? It's impeding the circular nature, and therefore wouldn't be circular. If I had a key ring, I think, well, that's, people call it a key ring, but it's really a key fob, right? Your little remote control fob that you have on your car or whatever, or if you had some decorative thing. I know a lot of girls I know have those rings on their keys so they can put it in their whatever. My wife and all my daughters have those things. Does anybody have those? Yes. Anyway, yeah, but the point is, if there's something attached to where the rings are, that attachment keeps the keys from being rotated around and matching another arrangement. So those kind of things take away the circularity, but wouldn't they still be flippable? So remember, if it's flippable, which I can't think of a ton of things, I can't flip a bunch of people around a table, right? Hold on, it looks just the same. Right? I'm not going to do that, but I can flip a charm bracelet, I can flip a necklace, I can flip keys. I can't flip tables, but they could all be circular, or they could all not be circular. So you're going to need to be able to understand the different situations on a test. And it could be something as similar as this, or simple as this. Like, what if I gave you a couple of examples right here. How many seating arrangements can be made for 10 people sitting at a circular table with 10 chairs? Does it sound like anything is impeding the circularity? No. So you would say, well, 10 people and 10 chairs. I'm going to go 10 minus 1, which is 9, factorial. Call it a day. Right now, if I change that to from 10 people sitting at a circular table, 10 chairs, to 10 keys on a circular ring, right? If I changed it to that, you'd go, oh, 10 keys on a circular ring, 9 factorial, but because it's circular, flippable, I divide by 2 as well. But this one is not that case. This is just 9 factorial. Come over here. How many ways can 8 charms be arranged on a necklace that has a clasp? What does the clasp do? Stops that circular ability to be able to rotate things and meet a different criteria. So I definitely can't say minus 1 factorial. I'm going to have to keep the 8 factorial. But what can I still do? I can divide it by 2 because it is a necklace, and necklaces, key rings, charm bracelets, whatever, are flippable in nature. So they don't have to both happen. One could happen, one could not happen, whatever. And if I get rid of the word clasp, what does that do? Then it makes it circular, and I would change that 8 to 7 factorial, but I would still divide it by 2 because of the flippable part. And it really is just that simple. Yes?
On test, could you just write the 8 factorial?
Or whatever, yeah, this original problem. Yeah, absolutely. Please don't simplify anything on this test. And there'll be one problem on there. I'm going to even tell you. It'll say something like, simplify 10C3. Simplify 11P2. Simplify 15 factorial over 12 factorial, 3 factorial. I'll give you some situations like this just to see if you can do the math. But when you'll see, when you do the math, it's not bad. I mean, this ends up being, what, 10 times 9 times 8 over 3 times 2 when you're done. This ends up being 11 times 10. This right here ends up being 15, 14, 13 over 3, 2. The math's not, after you cancel stuff, the math will not be bad on those. I'm just testing your ability to know the rules. But on a normal problem that asks you a question and doesn't say simplify, leave it, leave it, leave it, leave it. Don't do any simplifying. You're wasting your time because I literally will not, my key doesn't even have the correct answer. I will not look to see. And I think there's maybe only 1 or 2 questions in all of the work we do. I think there's one problem on probability, if we get to that, where I say, which card hand is the hardest to get? So what do you think makes that card hand the hardest to get? Like if you're doing a probability problem. It would have the low, well, depend if the numerators are the same, but it would have the lowest probability, right? So you, in that rare case, yes, you would have to pull out your calculator and type it all in there and get an answer and go, oh, this is smaller than that. This must be harder to get. But in the absence of that, and I probably shouldn't even have it on there, in the absence of that 1 or 2 times I asked that question, don't simplify anything. And I won't ask that on a test. All right? At this point on, these problems are all asking you different questions about counting principles. It's just more and more of the same old stuff over and over again. Okay? So we're going to do some of this today in class until the bell rings. Just hop from random problem to random problem. You're going to go to home tonight, try to do everything else you can possibly do. We'll spend a brief period of time answering questions tomorrow when we come back to class, and then we're going to jump into probability. Today's Wednesday or Tuesday? We're going to jump into probability on Wednesday. And if we do that, yes, we will be on pace. Yes.
I have a question about last night's.
Okay.
On page 86.
Number 12. Okay. A lot of people, I'll just say what the mistake a lot of people make is. A lot of people say, okay, 3 letters, 3 digits, find the number of license plates. So 3 letters, they go, well, you could have 26, 26, 26. By the way, don't go, you know, my parents work at the DMV, and that's not true because they don't use the letters O or the letters I. That isn't true. They might not even use Q, but that wasn't a part of our problem, right? So don't bring any extra information into a problem that you, like if we're dealing with a 52 card deck, don't go, what about jokers? I mean, don't do that stuff. We're just going to stick to what the problem is suggesting, which is letter, letter, letter. Now, a lot of people make this mistake right here. Everybody with me? Even the sleeping people? All right, so right here, the last 3 digits are supposed to be numbers. Now, if it didn't say anything about you can't have 0, 0, 0, the temptation would be to just do this, right? Well, when I put that 0, 0, 0 in there, people go, well, how do I get rid of that one situation? And by the way, I don't know what 26 cubed is. It's a big number, but I do know 10 cubed is 1,000, right? People make the mistake right here of going, oh, well, if it's not going to be 0, 0, 0, I can eliminate that just by making this a 9. But what happens when I make that a 9? That's 900 ways, 1,000. How many ways did I just get rid of? 100. I really only want to get rid of what? That one way. But don't subtract 1 from the whole thing. If I subtract 1 from the whole thing, what happens? Then I'm saying that if I just subtract 1 option, I'm really not doing the right thing. I need to subtract 1 of these 1,000. Are you with me? Because I could have 0, 0, 0 with every one of those. I mean, every single one of those 26 cubed options, can I? And that's a lot of options. So just subtract 1 from this and go 26 cubed times 999. All right, not to be mistaken with 9 times 9 times 9. Don't do that either, because 9 times 9 times 9 is way lower than 10 times 10 times 10, isn't it? I mean, significantly lower. Y'all with me? 729 and 1,000, you've subtracted a lot. So if the only thing you can't do is this, say, I want to get rid of 1 of the numbers, 1 of the 1,000 to 999. All right? So I'm jumping back to here. I'm just going to move through these. If you see one that you've already done and want to talk about, feel free to ask. But I'm just going to bounce around. Your job is to try to do everything else. So how about, we'll just do 28 and 29. How many unique ways can Johnny, Biff, Rhonda, Julio, and Fred sit around a table? There's 5 people, 5 minus 1, so 4 factorial. Don't even have to reduce. So that's it, because it was circular. Is the table flippable? No. If Johnny has to sit at the seat nearest the door, so you got this table again, let's just say the door is over here. Johnny has to sit there, and what is happening? What's happening? It's impeding the circularity. So what am I arranging now? The rest of the 4 on a linear situation. So what is that then? Just 4 factorial, which is odd to a lot of people because they're like, wait a minute. 5 people around the circular would be 4 factorial. And Johnny sitting there and the 4 people on the linear is also a 4 factorial. And sometimes these things hurt people's brains. How can that be the same? But we're sticking to the probability. And it's true, but we're sticking to the probability. Oh, I'm sorry, we're sticking to the counting principles. All right? What about Barbie has a claspless bracelet, and she wants to attach her 5 different charms to the bracelet. How many unique ways can they be arranged? 4 factorial, because there's nothing circular about it. I mean, I'm sorry, it's definitely circular. There's no class, so there's nothing impeding that, but it's also flippable. So it ends up being 12 different ways, but we don't care. 4 factorial over 2. Okay, what about number 30? This bothers a lot of people. 10 students in a class that meets in a room that has 12 chairs. All right? How many ways is it possible for the students to be seated? Say again. What things are going on here? There's a couple ways to do this. Imagine, right here, imagine 10 of you walk into my room. There's 12 chairs. There's 2 ways to think about this. What's the first thing you're going to do? So you guys are picking 10 of the 12 chairs first, right? So if I say that, does the order have an effect on the outcome? Okay, so I could say, for instance, all right, there's 12 chairs. There's 10 of you walk in the room. You get together and you decide, all right, let's definitely sit in those 10. And then, but it says how many different ways can you be seated. So then what can I technically do? Of the 10 ways to, now you've picked the 10 chairs, right? You're all different people. So in those 10 seats, this counts the number of ways you could pick the seats. Now, how many ways can I arrange 10 people in those 10 seats? 10 factorial. Now, look at this. What's the math on 12C10? 12 factorial over what? Not for combination. Over 2 factorial. What? 10 factorial times 10 factorial. What does that leave me with? 12 factorial over 2 factorial. Isn't 12 factorial over 2 factorial the same thing as 12p 10? So this is the same as this. Just 2 ways to think about it. This logic is 10 people walk in the room. Hey guys, get together. Which 2 seats are we not sitting in? Oh, those 2 in the back are terrible. We're not sitting there. Or those 2 in the front, we're not sitting there. Okay, now that we've decided what we're not sitting in, we're going to be sitting in, we chose 10 of the 12. The order doesn't matter which ones we picked. The order in which we picked them didn't matter. Now we're going to arrange ourselves. Well, that's the same thing as saying, wait, there's 12 things to pick. from. I'm going to pick the 10 chairs, and the order in which I pick them, which is kind of like the order in which the people sit, has an effect on the outcome. And that ends up being the same thing as this does. So you could get away with either one. Are y'all seeing that? But that's just because of the math. And it does kind of make it logical, I think. If you had 12 seats in a room and the 10 people are like, okay, there's lots of different ways we can choose the seats, but once we choose them, the order in which we choose them will be impacted by which people sit where. There's a lot of ways that can happen. That does it all at once. Yeah. Say it again. Nothing. I'm just trying to show you that the logic either way would be the same. All right, what about this one? I love this point. It's a huge math team question. I mean, it's not huge. It's whatever, 7 inches long, but it's like a very popular math team question. If I draw 8 points on a circle, right? So imagine a circle, and there's a key to this being circle right here. Don't just think circular just yet. Hold on. 8 points on a circle, and I start drawing triangles. How many different triangles could you draw? Now, by the way, imagine this. If I draw triangles, let's just say I pick that point and that point and that point right here. Does it matter which order, the order in which I pick those 3 points? If I pick this, 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 or this, 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 or this, 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 it doesn't matter. I'm still going to get the same triangle. So what am I really doing here if I count all the different number of ways to get triangles? I'm doing a combination. I'm picking what? 3 from the 8. There's 8 C3 ways to do that. And definitely a combination. Because whether I pick point A, then B, then C, or C, then A, then B, I'm still getting a triangle. Right? Wouldn't that be, and then why did they make it circular, do they think? Maybe. Let me rewrite this question. What if I said this? If I draw 8 points on a plane, what could go wrong here with 8 points on a plane? That's right. If those 8 points happen to have 3 points that were linear, then that would not make a triangle, would it? Are you seeing that? That wouldn't be a triangle. Those wouldn't be a triangle. I would just have a linear situation. So by saying they're on a circle, I'm eliminating the linear ability to not get a triangle. Are you with me? Yes, and you'll see that as well. It'll say if I draw 8 points, and it will say where no 3 are collinear. Like all I have to do is say no 3 because any 2 are, right? You can connect 2 points to make a line. But as long as no 3 are collinear, 3 or more, then you're safe. But a lot of times they'll just make a circle. Now sometimes they'll really mess with you. I love this problem. This is an old problem from many a math tournament. They'll give you this and they'll say 12 dots on a semicircle, and it could be a semicircle, it could be some figure, but they put a circular aspect and a linear aspect in it. Then they ask this question: by connecting any 4 dots, how many quadrilaterals can be made? And this is a great problem for talking about combinations and for talking about and or and what that means. Remember, when I do and, what do I do? And when I do or, I add. So let's think about that. So tell me, how can I pick 4 dots and make a quadrilateral? And if you say 12C4, is there a chance that I pick these 4? So that can't work. Is there a chance I pick 3 of these and 1 of these? That can't work. So what can work for me? So let's think about what she's going to say. She's about to say, I could have 2 on the bottom. So what are you doing? How many ways can I pick 2 on the bottom? Let's count. 4 to choose from. Choose 2. Does the order have an impact? No. Is choosing that and that or that and that any different? So I could pick 2 on the bottom, which would be 4C2, right? But if I pick 2 on the bottom, I would have to have what then? 2 there. How many are here? 8. So how many ways are there to pick 2 there? And am I picking these 2 or these 2 or these 2 and these 2? So times 8C2. 2 on the bottom and 2 on the top. That is definitely an option. Are there any other options? So you're saying I could pick this situation or what? 1 on the bottom? How many ways are there to get 1 on the bottom? 4. And you're welcome to put 4 if it's 4. But if you wanted to stick to the combination thing, you could say 4C1, which, by the way, is 4. So you can put 4 in there if it's 4. But if I pick 1 here, what do I have to have? 3 of those. And because those are not collinear, I am going to get an angle out of those, aren't I? But I would be picking 3 of those angles. Think about it. If I pick this one, and this one, and this one, doesn't that still make a 4-sided figure? Because I know no 3 of these are collinear. Okay? I'm struggling with that. So 8C3 been a good lunch, huh? All right. What else could happen?
Oh, yeah, 4 from the top.
Or I could get 4 from the top, which would be none from the bottom. And you're welcome to go 4C0. If you do 4C0, you get 1. So it doesn't impact it 1 times something, doesn't change anything. But I could pick 4 of those 8. Right? And that's the number of ways I could still do this. Such a common problem. This becomes extra hard. This is probably a ciphering question if it doesn't have multiple choice. Although that's written, it doesn't have multiple choice. But that's probably a ciphering problem. So you'd have to come in here and write all these things as quickly as possible. But if you get better at combinations, remember that little hint I told you about permutations? If you have 4P2, it's just the first 2 numbers in 4 factorial. Well, the only thing the combination does differently is divided by 2 factorial. So if it's me, I'm not right. I'm going the first 2 numbers in 4 factorial divided by 2 factorial, which is 2 times 1. The first 2 numbers in 8 factorial divided by 2 factorial, which is 2 times 1. The first 1 number in 4 factorial divided by 1 factorial. First 3 numbers in 8 factorial divided by 3 factorial. The first 4 numbers in 8 factorial, this is the one that probably gets a little tricky, over 4 factorial. And this will, at the very minimum, allow me to do this 6 times 28. Yeah, that's going to be a little tricky, but I can do it. Right here, 56 times 4. Yeah, sorry, times 4. That's a little tricky, but I can do it. This, 10 times 7, 70, not bad at all. And I can do the math on these and get to 462 probably pretty quickly. Maybe I get it in first place, maybe I get it in second. And if it's multiple choice, then I can certainly get it. Great problem to give it a math. The only thing that might be different on your test is I might say, what's the probability that if I connect 4 that I would get a count out of this? And all probability, but you don't have to do any simplifying, but probability just takes this and divides it by the total number of ways I can pick 4 from 12, which would just be this. That doesn't ensure quadrilateral, though, does it? That's just the total number of ways I can just pick 4 points, which if you remember from that definition of probability, it's the number of ways you can be successful over just the total number of ways, successful or not successful. But that is not our answer here because it just says how many. Y'all seeing that? Just pick some random things. What about this? A bag contains 4 red, 6 white, and 9 blue marbles. How many ways can 5 be selected if they all end up being white marbles? Now, if I pick 5 marbles from this bag, how many ways can they all be white? Now, does the order in which you pick them affect the outcome? How many white ones what are you choosing from? If they're all white, you're essentially doing what? Hold on, it's not a probability. What are we technically doing? I am picking what? All 5 from the what? just the 6 whites. Because if I pick them from all 19, am I guaranteeing that they'll be white? I'm not. That would tell me how many ways I could pick 5 marbles if I went 19C5. But I'm just going to go 6C5, which when you do the math on that, you get 6, which makes really good sense. Because think about it. If I have 6 marbles and I have to pick 5 of them, I'm going to leave one of them out, right? How many ways can I do that if there's 6 white marbles? I can leave this one out, 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 or this one out. There's 6 ways, and that's what I end up getting. That's what this gives me, 6. What about if they're all blue? You're picking them all from which ones? The 9 blue ones, so 9C5. Order doesn't matter, right? I don't pick these up and go, oh man, I got these 5 blue marbles in the wrong order. I mean, if all I want, like if you're picking, I don't know, Starburst out of a bag blindly, and you love the pink ones, and you hate the yellow ones, right? And you picked all pink ones, so you go, ugh, wrong order. No, you got your 5 pink ones, you're happy or whatever. What about exactly 2 must be blue? Now, when I say exactly 2 must be blue, what am I assuming then? I got to pick 5, right? So that means the 3 others would have to be what? Not blue. So that would mean I'd be picking 2 of them. If it says exactly, I have to pick 2 and only 2, right, from the blues. How do I do that? Pick that for me. 2 of them from the blues. So 9C2. And then the remaining 3 come from the what? They're not blues. Because if I, this is the mistake people make. They went, well, I picked 2 of the blues, so there's 17 left, 17C3. What's wrong with this? Some of these might be blue. There's no guarantee that they're not blue. And this says only 2 of them are blue. Exactly 2. Any more than I wouldn't have exactly 2. So I have to pick the 2 right here, those last 2, not from any of those, but from these. Now, if you're asking yourself right now, well, how do you do that? If you're blindly picking out of a thing, how do I assure that? I'm not saying what's the probability that it happens. Or I'm not saying that it's likely that it's happened. I'm just asking how many ways, if it did happen, how many ways could it have occurred given the situation you have? Yeah, it's totally unlikely that I reach into and grab 5 marbles and I get that. Totally unlikely because there's so many other options. But if it did happen, there's this many different ways it could have happened. What about this? 2 or 1 color, 3 or another. This is a nightmare. Doubt I'd ask you this on a test. But 2 of 1 color, 3 or another, what are my options there? I could have what? 2 reds, and then what? 3 whites, or 2 reds, 3 blues, or 2 whites, 3 reds, or 2 whites, 3 blues, or 2 blues, 3 reds, or 2 blues, 3 whites. And then you'd have to come in, and those are all the options, right? Then you'd have to come in and figure out each one of these. Like, how many ways can I do 2 reds? 4C2. And how many ways can I do 3 whites? 6C3. Or, plus, how many ways can I do 2 reds? 4C2. And 3 blues. 9C3. And you'd have to just plug your way through that situation. Which, again, I'm not going to be tedious like that on a test. This is just trying to get you to think. Scrolling up a little bit, I got a couple minutes. What about this? 8 men, 10 women. It says from a group of 8 men and 10 women, I'm picking a 5-person committee. So I know I'm picking 5 people. How many, not probability, how many committees could be formed, and I'm jumping to 45, if 3 are men and 2 are women? Well, think about it. If I'm trying to pick a committee and I want 3 men, am I looking at you or you or you? I'm just not. I'm looking at the men if I'm picking from the men, and I'm looking at the women if I'm picking from the women. If that's my goal to do that, right? So think that way. It's kind of like in a card game. If I say something like, how many ways can you get two kings if you pull cards from a deck? And I put all the cards face up, right? Am I looking at the queens and the jacks and the tens? No, I'm looking at what I want. So if I'm trying to get 3 of these from 8 of these, what do I need to do? 8C3, that's how many ways I could do that. How many ways can I get that from that? 10C2. And do I want to do this or this and this? And. How about this? A student is to choose and answer 10 of, Bell's about to ring. Do the best you can on these. If you have questions, bring them in tomorrow. We're going to answer those questions and head into probability, which I hope that you see is not a whole lot different than this. If you're still counting. Although there's 2 ways to go about it. Can you come the next 3 days and check?
Oh, so probably not. Well, because it's gas.
Not good. You struggle with qualifying your stuff? Yeah.
Well, yeah, I just like didn't do well this week because like after COVID, like no longer. So, and then I got an inhaler and I like actually improved a lot. But I was making kind of too late by then. So, yeah. I guess we haven't like fully anything, so. I don't need
Yeah.
Oh, it's fine. Oh my gosh, it's
Yeah.
Yeah. Yeah. So how was it? 11 days before it was
I will see the best on
like, so fake. Chat me.
Oh, no. Oh, you, no, not playing. Good. Try Reese's Pieces. I would be honest, I don't intimidate me. You probably I put my body on the line.
The best idea.
Not really.